welcome to this explainer. We're going to do something a little different today. We are going to completely strip away all the marketing hype, the buzzwords, and those sci-fi narratives you hear everywhere about large language models. Instead, we're going to open up the black box and look at the actual math and the pure mechanics powering these systems. If you've ever wondered what is literally happening under the hood of a tool like GPT or Claude, you are absolutely in the right place.
You know, it's so easy to interact with these models and feel like there's a literal ghost in the machine, but I want to hook you right away with this fundamental truth. There is absolutely no magic here, none at all. What we're actually dealing with is linear algebra, probability, and an extraordinary, mind-bending amount of compute. By the end of this explainer, you're going to understand exactly how those three ingredients combine to create the illusion of thought.
Okay, let's dive into this. We'll start by decoding the black box, then look at turning language into geometry, explore the power of self-attention, break down pre-training and scaling laws, discuss creating a helpful assistant, and finally wrap up with features, flaws, and futures. All right, Section 1, decoding the black box and establishing the core objective. If you strip away the sleek interface, what you are looking at is an autoregressive model. Simply put, it's a system that estimates the probability of every possible next token, or piece of a word, based on the text it has seen so far, and then it just samples one. That's it. That is literally the entire generative act. It just repeats this ridiculously simple objective, one single token at a time, until the response is finished. But here's the truly fascinating part. If you train a network to be exceedingly good at predicting the next token across trillions of words, it has to implicitly learn grammar, facts, and human reasoning patterns just to make accurate predictions. The objective is completely trivial, but the internalized knowledge required to actually achieve it is profoundly complex.
Moving right along to Section 2, turning language into geometry.
Here's the thing. Models don't actually see words at all. They see tokens. Algorithms like byte-pair encoding take a word like unbelievable and slice it into subword chunks like un, believe, and able. This is actually a brilliant approach because it lets the model handle typos or brand new slang by just recombining familiar structural pieces. But step 3 is where the real transformation happens. Each token is mapped to an embedding. Think of this as a high-dimensional vector, typically a few thousand numbers long. These numbers place the token into a vast geometric space where physical closeness actually equals semantic meaning. So words that mean similar things are physically grouped closer together in this giant mathematical space. There is a quote from our source material that I absolutely love because it just hits the nail on the head regarding the reality of AI. It says, "Language has been converted into geometry. From the very moment those tokens are embedded, the model never looks at language again. Every single layer of computation that follows operates strictly on those vectors. It's navigating a map of numbers, not a dictionary of words." Which brings us to Section 3, the power of self-attention and how we connect context. In the past, to understand context, models had to read sequentially, word by word. It was clunky, it was slow, and honestly, they'd forget the beginning of a long sentence by the time they reached the end. Self-attention completely changed the game. Let's take the sentence, "The cat sat because it was tired." For you and me, it's completely obvious that it refers to the cat. But for an algorithm, that requires serious computation. Self-attention lets the word it look at every single other token in the sequence simultaneously to figure out exactly what it connects to. So what is actually happening under the hood here? Well, every token produces 3 distinct vectors: a query, a key, and a value. You can think of the query as a token asking out loud, "What am I looking for?" The key is essentially broadcasting, "Hey, here is what I offer." And the value holds the actual underlying information. So for the word it, the model calculates a dot product, which is really just a mathematical measure of similarity between the query of it and the keys of every other word. It finds a massive similarity with the key for cat. It takes a weighted average, and suddenly the mathematical representation of the word it is instantly enriched with the concept of the cat. And it doesn't just do this once, not even close. This self-attention computation happens in parallel across tons of attention heads, with each one specializing in different things like grammar or topic relevance. Then that data is passed through feed-forward networks, and this entire process is stacked. We're talking dozens, sometimes over 100 times. Each stacked layer builds progressively more abstract representations. The early layers figure out basic syntax, while the final layers are capturing complex factual associations.
Architecturally speaking, this massive stack of layers is the entire model. Everything else is basically just plumbing.
All right, let's zoom out a bit for section 4, pre-training and scaling laws.
Pre-training is the phase where a model essentially speed reads massive fractions of the entire internet. It guesses the next word, gets penalized if it's wrong, updates its parameters, and repeats this process trillions of times. The decrease in error, what engineers call the loss curve, is astonishingly predictable. It reliably drops as a smooth mathematical function based on 3 core pillars: model size, dataset size, and compute. This predictability is really the financial bedrock of the entire AI boom. It's exactly why tech companies confidently invest hundreds of millions of dollars into a single training run before it even finishes. The math tells them exactly how smart the model is going to be when it's done. But while the error rate predictably shrinks, the actual behaviors of the model do something truly wild. As you cross certain massive thresholds of scale, complex abilities seemingly just emerge out of nowhere. Suddenly, the model can do multi-step arithmetic, or translate between rare languages, or even write Python code. The craziest part? The underlying training objective, just guessing the next token, never changed. The model just got big enough that developing these complex skills became the most statistically efficient way to guess the next word correctly.
Section 5, creating a helpful assistant out of this raw predictive engine.
This highlights a pretty funny problem we face after pre-training. A raw base model is not an assistant. If you give a raw base model a prompt, like a question, it might just generate 5 more questions. Why? Because mathematically, on the internet, questions often follow other questions. We have to essentially align the model so that it answers the prompt directly, politely, and helpfully. We have to shift it from being a statistical parrot into a functional, reliable tool. This alignment happens in a few crucial steps. First up is supervised fine-tuning, where researchers feed the model thousands of highly curated, human-written examples of perfect Q&A formats. Then comes the real secret sauce, RLHF, or reinforcement learning from human feedback. Humans literally sit down and rank multiple outputs from the model. They say, this answer is better than that one. A separate reward model learns what humans actually prefer, and then automatically scores the language model, pushing it relentlessly toward behavior that is helpful, honest, and harmless. Which brings us to our final stop. Section 6, Features, Flaws, and Futures. Let's look at the real-world mechanical results of this architecture. On the plus side, we have incredible in-context learning. Because the model is heavily trained to track patterns across its context window using self-attention, you can just type a few examples of a totally new task right into the prompt, and the model will instantly generalize and do it. No retraining required. But the downside? That exact same attention mechanism scales quadratically. Every new word has to calculate its relationship to every single previous word. That is exactly why long conversations eventually break down or cost an absolute fortune. It's a massive finite engineering bottleneck, not just some random product glitch. And then, of course, may have to talk about the elephant in the room. The crucial point here is that we really need to reframe how we think about hallucinations. A model confidently giving you fake information is not a bug that a programmer can just easily patch away in the next update. The model has absolutely no built-in concept of, I don't know. When its training data thins out on a specific topic, the engine just keeps doing exactly what it was built to do, fluently generating the next most mathematically probable token. It generates plausible but false statements as a direct, inescapable mechanical consequence of its core objective. So, there you have the machine. We've traced the tokens as they become geometric vectors, we've watched self-attention gather context, seen the massive stack of layered computation, and explored how next token prediction at an unfathomable scale creates the AI we see today. It is a remarkably simple recipe when you break it all down, but I want to leave you with this final, truly provocative thought. If everything we just went through is genuinely just predicting the next token through geometry and scale, how does something that looks, acts, and feels so incredibly much like actual human reasoning emerge from it? It remains one of the most profound open questions in science today, and it proves that in the world of AI, the math itself might just be entirely indistinguishable from magic. Thanks so much for joining me on this explainer, and keep questioning the mechanics of the world around you.